Hello everybody, my name is Justin Mansell and I'm going to be giving you a quick tutorial on the control matrix generation software from Active Optical Systems. In this tutorial, we will go over how to load a DM file, wavefront sensor file, and poke matrices into the tool, evaluate and condition the control matrix using the series of steps that are indicated in the tabs, and then generate and save that control matrix for use outside the software. So when you load the software, this is what you're greeted with. There's a button up here in the top left to load the DM file. So we can do that by going to our data set here and loading up the DM file. So this is the DM configuration that we're working with. Then there's an option for loading the wavefront sensor file. Again, I have this data set on my desktop, so I will load that up. Depending on how your data file was saved, you may or may not need to transpose it. I happen to know that I'm not going to do that for this one, and I'll show you what the ramifications of that are. And then you're loading a poke matrix. I'm assuming that the poke matrix was measured with full 100% strokes. If it wasn't, you can put the measured poke magnitude into this. You can also have it remove the average slope if you want to remove the tilt control from your deformable mirror. I'm not going to do either of those things. I'm not going to adjust either of those. I'm just going to load up the poke.csv file, again from this data set on my desktop. There are two different ways of typically recording a poke matrix. You can do it in XXYY format or XYXY format. This has to do with how the data was put into the file itself. I can show you, I will pick one of these arbitrarily and I'll see if I get it right, and I'll show you how to check for that. So we'll say, sure, change it. Turns out that this looks correct. I can cycle through now the influence functions and it will show me the slope magnitudes in both a quiver plot format and in a slope magnitude format here. This is the matrix that was loaded in. If it is an XY, it looks about like this. If it is XXYY, it'll look segmented. So long story short, this looks correct to me. And so now we can move forward to the next steps. You can also load in an intensity vector. This is optional, but this will allow you to intensity weight your subapertures. In this case, we're not going to do that. You can use this button here and this numeric up down here to cycle through and pick arbitrary actuators. Let's pick number 77. Number 77 looks about right. So I think we're in pretty good shape here. This button here pops up a dialog box that allows you to walk through the basic process flow. This tab is used for generating an ideal poke matrix. So what you need to do is line up the wavefront sensor subapertures with the DM actuators in order to use this tab. So you can move the actuators around in the grid. What you're looking for typically in a free geometry is for the subapertures to be on the corners of the intersecting actuators. So I'll play with this for just a minute to show you how it works. You can adjust the magnification. What we're trying to do here is, let's assume we're trying to get to a free geometry, and I'm trying to get the magnification between these two files set up so that they look about right. This looks pretty good. I'm going to slide it to the side here a little bit, well, maybe a little too much. Slide it down a little bit. And this looks pretty reasonable. You can zoom in on this plot. You can make a lot of these plots bigger or smaller by adjusting these positions in the split containers. You can rotate it and flip it if needed, because sometimes optical systems will rotate and flip. And you can adjust the magnitude of the poke here. I'm sorry, this is the size of the poke here. So let's just assume that this is about right. I probably would spend a little more time on it if I were actually trying to make an ideal poke matrix out of this. So I will say make an ideal poke matrix. That looks pretty reasonable to me. It doesn't quite look like the one we generated, or the one we loaded. So let's try rotating this. You can rotate it like that, or you can just type in values. I'm going to say, okay. And now let's see what it looks like with 90 degree. How about 180? So I think that I'm going to say don't flip it. And now we're starting to look a lot like the matrix that we loaded. There we go. That's the kind of thing that we're looking for here, because it looks a lot like what we're seeing here. So now I've created an ideal poke matrix. I can save that out and process it if I want to. I'm going to make sure that I'm using my measured one by going back to here and loading up the poke matrix again. And again, taking a look at these influence functions. That looks pretty good. So this allows us to generate ideal poke matrices based on theory, and be able to save those out and load them back in and process those. Poke filtering. This is a newer feature. It basically goes through and tries to zero out any low values. There's a little description of how this works here. It can also do fitting to Gaussians and has some actuator scaling things here. We're not going to play with poke filtering today. I will say unfilter the matrix, and we'll go to alignment. What this does is it generates a position map of the location of each of the subapertures. Each of the actuators in the subaperture grid. And again, you're in a situation here where it's tough to see this, so we can make it bigger by playing with these. You can also zoom in on it. Turns out that this was an ideal generated matrix, so everything lines up perfectly, and we've got the actuator locations right in the center of the 4 subapertures. This is perfect, looks really good. If you are working in a laboratory environment, this will be useful for helping to facilitate the alignment between your actuators and subapertures, which is typically manipulated with a pair of steering mirrors. This shows the waffle in the slope magnitude. It should look pretty flat like this. And this is the waffle generated command set. And so this is another newer feature for us. What we're looking for in perfect freed alignment is something that's pretty flat like this. The edges are going to be a little goofy, but that's because the actuators don't span all of the subapertures toward the edges. Okay, so now there's reduced subapertures. In a real system, what you oftentimes find is that the edge subapertures are poorly illuminated. And sometimes, if you're working in a complete square grid, you have a bunch of the subapertures at the edge entirely unilluminated. So you want to remove those. With a variety of ways of doing that. What I'll show you today, we talked about loading an intensity matrix or a vector early on this load data page. We did not do that, so it assumes that the intensity is always 1 for all of this. It will also calculate for each of the subapertures what the slope magnitudes are. And so what you find is that poorly illuminated subapertures typically have either very high slope because they're really noisy, or very low slope. So you can set upper and lower limits for filtering those out. Let's just raise this one up. This happens to, again, be an ideal set. So I can raise this up and hit the reduce button. I'm still not killing many of these. Let's bring it up some more. There we go. Turns out I don't have to hit the reduce button. I forgot I fixed that. And so now you can just bring this up, and it'll start eliminating the lower amplitude measurements here. So you can do it based on amplitude. I'm going to bring this all the way back down to 0 here, so we're not eliminating any of those. Now we can also take a look at this feature, which is a newer feature that we put in. And this allows us to impose on the system a subaperture radius. So let's see if I can hit this guy. There we go. So now I can specify This one you actually have to hit the button for. I can specify a radius and have it remove anything outside of that radius. I can also, let me bring this back down so that it's a smaller one here. I can also move that around. And I can slide around my clip aperture and just eliminate the edges. This is pretty common that you want to go and eliminate the edges, so we built this feature in so that you can just apply this filter and eliminate all the sub apertures at the edges. Now we can move on to actuator slaving. Again, we're in a situation where if we have a poorly illuminated actuator at the edge, we may want to slave that one out. Also, the same radius feature is built in here. Let's bring this radius up to 100% or more, and we can eliminate that one. It's left one of them eliminated. We can go through here and make adjustments to which sub-apertures and actuators we want to eliminate with these two tabs. When you are happy with the way you've configured the slaving, let's just slave out these edges here. You can see that what we're doing here is we're generating a matrix that links actuators to its nearest neighbor. And that's this matrix here to remove the slaves. This is the matrix to put it back in. And this is the revised poke matrix after slaving. And this is the slaving map. So you can see that these various actuators are slaved to their neighbors. So we'll keep that in there for now. And now we're on to creating a control matrix. So you can hit the Make Control Matrix button. It will go through and apply all of the settings you've put forth in the previous tabs. You can force it to 0 eliminated sub-apertures. Of course, we didn't eliminate any, so it doesn't do anything for this one. You can remove modes. So I can remove a couple of modes here and start to clean this matrix up a little bit. And then when you're going to save it, you can scale the control matrix by a scale factor. This is important if you're trying to do fixed point math in an FPGA, as we are in some of our control systems. This is a pretty typical number to use, this 32,767 number, which is just shy of a power of 2. 768 is the power of 2 for that. And then you can save the control matrix. It pops up a nice dialog here. I'll go back to my desktop data set and say control matrix, and it will save out a whole bunch of control matrices. So let's take a look at that. So if I look on the folder in my desktop, I can see that I just generated a bunch of these files. There are times in which various softwares will read them in different formats. Again, there's the XY versus XXYY formats. Then there's different negation formats. So if the control matrix is supposed to be negative because you can't adjust your gain to accommodate it the other way, we have a negative one that's saved out, and then we have a transpose one that's saved out. And this should address the vast majority of needs of most softwares. Most of the things that we do require one of these typical formats. I believe it is the XY format for a lot of the things that we do, but we can pick any one of these, and they're all the same data, just in different slightly modified formats. So going back to the control matrix generation piece, another thing that you can look at once you've generated a control matrix is these single value decomposition modes. And so you can see them showing up here in both the DM format and in slope magnitude format. Sometimes these are important for people to see. Other times they don't need to see them. They just need to run. There's one other feature that's built into here that's worth talking about relative to control matrices, and that's the spatial filtering. So what this does is create a Gaussian convolution filter at each of the actuators, and then can apply that to the control matrix to minimize some of the highest spatial frequency terms and facilitate, if it's set properly, the interactuator stroke limits. So in this case, I've chosen a Gaussian size in the DM actuator spacing multiple of 1. And so you can see here it looks like an identity matrix almost, with some edge pieces here. And when I then go through and make the control matrix, it applies that to it, and I can save that out. So that's the spatial, oh wait, I'm sorry. once I've made the control matrix, I can apply it to it. You can see the filtered version, and I can save it out by clicking the Save Filtered Control Matrix button here. So this is some code we've written in order to test fixed point multiplies. For the most part, this is not useful for external customers. It's something that we use internally. And then we have code here for testing a control matrix. I won't go into detail on this, but you can load up a data set of slope vectors, feed it into this, and have it scan over leak and gain to determine what the optimal leak and gain values would be. So that is the basics on how to use the control matrix generation tool from Active Optical Systems. If you need any help with this, don't hesitate to contact us. The website is www.aos-llc.com. Again, my name was Justin Mansell, and thank you all for